Hello everybody, and thank you for joining me. Root Beer here, and we're going to start another contest, the 2004 Euclid contest. So this is the grade 12 paper, the big scholarship paper. It's the one everyone wants to do really well on, because, you know, you can be offered prize money, or scholarships at least for it. So we're going to do what we can. It's different to, say, the Pascal, Cayley, and Fermat in that it's written. So it's very similar to the Fryer, Galois, and Hypatia, the grade 9, 10, and 11 written contests from Waterloo. So if you're looking for additional practice and you don't have enough Euclids lying around, you can try past Hypatias, past Galois, that sort of thing. If you'd like a copy of this Euclid lying around, you can click the link in the description. You can get a copy for yourself. I do encourage you to try it out before you end up watching these videos, just to see how far you'd make it. Okay, well, let's take a look here. So the 2004 Euclid, and we're just going to skim through. You should always read through the contest. That's what you should be doing before you actually open the booklet and do it. And the time before the contest starts, read through, make sure you understand how much time do you have. Calculators, are they allowed? What's the deal with that? And for the Euclid competitions, just be aware, short answer, there are some short answer questions where you just need the final answer. And that's all. We're still going to show our work in these videos because that's good practice for the full solution ones where you do have to explain everything, you have to justify things. That's how you get the full marks. Okay? But I'll leave you guys to read that sort of thing on your downloaded copy. We're just going to jump into it right now with question number 1. It's got 3 parts, A, B, and C. And we're going to go through that. So, I've got my pen ready. Hopefully you've had yours ready. You've already given this a shot. And we're going to open up our notepad and we're going to get this started. Okay, so Euclid 2004. Alright, so let's read that first question. 1A. In the diagram, what is the area of figure A, B, C, D, E, F? Okay. So I got this figure. It looks, it's going to be a hexagon, although it's a very right-angle-y hexagon. So my bet is we're probably going to chop this up into areas that we're familiar with. Rectangles, triangles, that sort of thing. And I think we're definitely going to be cutting this up into rectangles. We're given some lengths, but not all. So this question is really, can we work out the other lengths and get the area? Okay. So let's copy this over into our notebook. Fantastic. So we got A, B, between those was 4. There was another 4 here. C, D, E, and F. We're told AF is 8. And I think that's all we had. Although we did have just a ton of right angles here. I think that was it. Is that the complete diagram? Yeah. Oh, there was an 8 on the bottom with FE. Okay. So, as with most things, most areas, if you're not sure exactly a formula to calculate it, the best thing to do is break it up into smaller areas that you do know how to calculate. Or a technique that's often used is not so much break it up into smaller areas and add them up, but figure out how to realize this particular area as a sum or difference of other areas that you're familiar calculating. Okay? So a big rectangle with a small triangle removed, you figure out the area of the big rectangle, subtract the area of the small triangle, that sort of thing. So we have lots of approaches here. The one that jumps out to me immediately would be sort of chopping it up maybe like this, or like this, something like that. Another thing you could do is maybe realize, well, hey, this is just a giant rectangle with a smaller rectangle cut out. These are all fantastic ways to look at the problem. Okay? So, what I'm going to do is I'm going to create a brand new point G here. And I'm just going to sort of chop him up. So, A, B, C, D, E, F. Well, that's really just the area of A, B, G, F plus the area of C, D, E, G. Okay? 2 smaller rectangles that I can work with. So now, ABGF, that's this rectangle, and I know he's got 4 by 8. So that's fantastic. Now the question is, can I work out CDEG? Well, you'll notice I have none of his side lengths, but since ABGF is a rectangle, we know there's a 4 there. This whole distance is 8, so GE's got to be 4. By the same reasoning, we'll get DE is 4 because we'll need 4 plus 4 to give us all 8. And if you wanted to, you could write that out more, but again, it's a light bulb question. We just need to show a little bit of work, get that final answer. That's how we earn marks here. Okay. But if you want some extra practice, by all means, explain. Because it's a rectangle, AB has got to be equal to GF. That sort of thing. We calculate 32 plus 16, and we are done with 48. So that would be our answer for the area of ABCDEF. Okay. It'll obviously take you less time because you're not explaining it in the video online, but there it is. Not a very difficult question to start us off here. Alright, 1B. Again, we just need our final answer. Always make note of that when you're doing Euclid, just because you don't want to be spending a whole lot of time doing a rigorous, nice, neat write-up of a question, and then, oh, it was a light bulb all along, I just needed to put 25, or whatever the answer was. Okay? Don't waste your time. Always be mindful of what you need to be doing. Okay, in the diagram, ABCD is a rectangle with AE 15, EB 20, and DF 24. What is the length of CF? Okay, so I'm going to copy this over to my notepad. So we're told it's a rectangle. We'll get right angles all over the place. And we have one, I believe it was a right angle triangle, 15 and 20 here. Well, if that is a right angle, then we should be able to get the length of the hypotenuse, which is just the side of the rectangle. So A, B, C, D, E, and F there. So we should be able to get length AB, and from that learn length CD. A, B, C, D, E is in here. And then we have F up here, and this was 24. This was also a right angle. Okay. So, let's see here. CF squared plus 24 squared is the same as CD squared. But CD squared is the same as AB squared. And AB squared, since we got a right angle triangle here, is 15 squared plus 20 squared. Okay, so you could have also just done it the other way, diagram chasing, figure out AB, then say what is CD, but when we look at it this way, we want CF, let's get an equation with CF, that leads us to what's CD. Well, CD is the same as AB, so what's AB? So we're working backwards. But now we have all known numbers, 24, 15, 20, the only thing we don't know is CF. So I could say CF squared is 15 squared plus 20 squared minus 24 squared. Just rearranging that. What AB and what CD is ultimately doesn't matter here. You can work them out. I think it's 25. AB and CD are 25. And you could certainly do that. Calculators are allowed, so by all means use that. But we don't actually need to, we don't care what AB really is. We really want CF. So CF squared, 15 squared, if you need to, grab your calculator. And you got 15 squared is 225, 20 squared is 400, and 24 squared is 576. Okay. So we get 625 minus 576, and that was likely you're not going to be doing that one in your head. But you could say, well, 575 is 50 less than that, so it's really 50 minus 1. It's going to be 49. If you need to, if you didn't bring your calculator, by all means, go old school, line them up like this, and you'll still get 49. Okay? But once we see CF squared is 49, then we say CF is 7. And we're done there. Okay. So we still have a C part to do, and that's going to be a big written answer. So we're going to have to be careful. We're going to have to justify. We're probably going to be wanting to use complete sentences here. So 1C. In the diagram, ABCD is a square of length 6. Points E, F, G, and H are on AB, BC, CD, and DA respectively, so that the ratios AE to EB, BF to FC, CG to GD, and DH to HA are all equal to 1 to 2. So EB is twice the length of AE, that sort of thing. What is the area of EFGH, this smaller figure in here? Which, just based on my picture, is a little stretched out. One might think it's a rectangle. I'm actually going to bet that it's a square as well, just based on the high degree of symmetry here. But if we think it's a rectangle or a square, we are going to have to prove it. So, what to do? Well, I know the side lengths of this square are 6. If I said AE is 2, thanks to this ratio stuff, I know that EB will be, not 2, x. EB will be 2x. It actually turns out that AE is 2, but I'm saying things before I've worked them out, so we're going to have to justify these. So let's draw our picture. A, B, C, D, and then we've got our points E, F, G, and H. Okay. So I could say something like, let AE have a length of X. Then since AE to EB is 1 to 2, EB has a length of 2x. AB is 6. AB is AE plus EB, which is x plus 2x, which is 3x. So 6 is 3x. X equals 2. Then, rather than having to calculate all the other ones out, I might simply say something like, similarly, AE, B, or we might, let's leave off the AE, but similarly, BF, CG, these are all the same length. EB is twice 2, so it's going to be 4. And F, C, G, D, H, A. All these guys are also equal to 4. Fantastic. Okay? So, we've done what I like to call a little bit of diagram chasing. We took some information, used it to get other lengths, angles, that sort of stuff. But we actually haven't approached the thing that they're asking for. They asked for the area of EFGH. Okay? So that's what we need to work on now. Now, we've got more information in our picture, but we actually didn't approach answering EFGH because we haven't figured out a plan of attack for that. We need to figure out EFGH. How could I figure out the area? Okay? And there's a couple ways we could figure out the area. 2 come to mind right away. I'll show you them. Okay? Maybe you thought of one and the other one's going to be brand new for you. But one thing we can do, this won't be part of my nice, neat write-up, but one thing we can do is we can say, well, we've got 4s and 2s and right angles. It's not that hard to show that all these lengths here are the same. It's also not hard to show that all these angles here are the same. And if these angles all work, we'll get right angles in here, and so that EFGH is a square. Okay, but that takes a little bit more justification. So that's probably the way I would have done it when I was younger. But remember what I said before. A great way to calculate areas that you don't know a whole lot about is to recognize them as bigger things with smaller things taken away, or a bunch of smaller things added up together, that sort of thing. Break it down into figures that you are familiar with, that you do know. And this would be great, but we have to fuss around a little bit with angles. So let me show you the way I'm going to approach it today. So what do we want? We want this thing here, which does turn out to be a square. We could certainly do this and show that it is a square. But that area is going to be this big thing here. You can see he's trapped inside there. He's this area. But it's also got these, to make the big square, we have all of these identical triangles, right-angled triangles, mind you. So it's minus, so we subtract off each of these triangles here. And these triangles, we know a base and a height for them, for each of them. And we know the side length of the big square. So we can do the area of the big square, subtract each of these four smaller areas, and what's left is EFGH. We don't have to know that it's a square. We don't have to know that it's rectangular. No right angles, nothing needed to be done. Okay? And maybe you thought of that way too. Maybe you didn't think of the diagram chasing the angles and showing that it's actually square. And maybe that's new for you too. But now we've got two different ways. And I really like it when a question has multiple options. Even if they're somewhat similar, just multiple avenues to get to the right answer. But this is the way I'm going to do it for you right now. Okay. So we have to justify it. I'd say the picture's okay. Explain the picture a little bit more. Again, we're going to ignore this stuff. That was another way to do it. But I might say something like, notice area of EFGH is area of, and I might remind them that it's square ABCD. With the four right angle triangles removed. Okay, picture's great. Explain it a little bit. I mean, that's one sentence, not a whole lot to do. You could even go a little further and say, well, based on this this length work that we did, all of these are going to be the same. So we're gonna make a note of that. Each of the four triangles has legs, which are the sides of the right angle triangle that are not the hypotenuse. That's a term some people don't know that you call them legs. Legs of 2 and 4. And so that makes them congruent. And since they're congruent, that means we got same area. So EFGH is big square ABCD. We might even put his side lengths in here. It was C here and then D. Minus 4 copies of this same triangle. Okay, not hard to do now. 6 squared minus 4 copies of base times height over 2. That's 36 minus 16, 20. We don't know it's a square. We haven't justified that. So we might say the area of quadrilateral. EFGH is 20. Okay? But alternatively, we could have gone through, shown that we've got right angles here. That's not particularly hard to do. And then 2 squared is 4, plus 4 squared is 16. We'd get 20 squared, so we get root 20 squared is these side lengths over here. And since it's a square, just square that, we'd get 20 that way too. Lots of different ways to do this question. There might even be more. But that does it for question C here on the 2004 Euclid. I think that's a great start, and we're going to look at question number 2, but we're going to do that in the next video. Thank you guys for watching. I hope you continue to watch the 2004 Euclid, and I'll see you for the next video next time. So long.